now?
Yeah, we can see.
Perfect. And the presentation?
Yep.
Perfect, thank you. So I'm talking about opportunities of biochar compost production and its use as organic fertilizer. This idea was developed in a research project called ClimEtSan, which was conducted between 2017 and 2021 in the frame of funding by German Ministry of Federal Ministry of Education and Research and the German Exchange Service in Ethiopia. Here we worked together with Hawassa University and wanted to develop a closed-loop system. The background is that until now, we have the situation that the wood that comes from the forest is usually used in most developing countries as like Ethiopia for cooking on open fire. And the food produced is usually used and excreted and then dumped in toilets into the open waterways. The organic waste is mostly dumped on dumping sites. So this causes the cooking on open fire causes carbon dioxide emissions and smoke. And the dumping sites, we have emissions of methane and nitrous oxides, all of them potential greenhouse gases. Nutrients get lost and even pollute the waterways, like nitrogen, phosphorus, potassium. And this is true for the excreta dumped in the water, but also all waste dumped on the dumping sites. But at the same time, we have a depletion of nutrients and soil degradation in the fields. And as a consequence, the soils are eroding and degrading. So, and with increasing fertilizer prices, this becomes a bigger and bigger problem. At the same time, we have the pathogen load from the human excreta and the smoke from the fires that cause a lot of health problems. With regard to the cooking, because this is what I want to focus now on this presentation, this is the reality in Ethiopia. The women cook on open fire and are exposed to the emissions. And worldwide, it's for a lot of countries the same situation. 2.4 billion people cook on open fire, and we have 3.2 million deaths related to this exposure to the smoke. Up to 2.4 gigatons of carbon dioxide emissions are mitigated per year. And when we introduce improved cooking stoves, we could reduce this drastically. Ethiopia, where 92% of all Ethiopians cook on open fire, is a good potential market for that. Here, 54 million tons of wood are burned every year, so the potential of avoiding carbon dioxide emissions is huge. Our aim is to close the loops by introducing biochar cooking stoves that reduce a lot of emissions, that reduce a lot of the wood needed. And we produce compost from this biochar together with the waste from ecological sanitation toilets and bio-waste, organic waste. So we have agriculture where we produce the harvest. It is food is produced by with the help of these biochar stoves, and the organic waste from cooking together with the excreta are composted together with the biochar from the cooking stoves. And this compost goes back as hygienic, safe, and nutrient and humus-rich fertilizer to the soils. Here we have an increase of soil fertility and at the same time a carbon sequestration, so win-win situation in a lot of different dimensions. At the same time, we reduce smoke and carbon dioxide emissions and methane and nitrous oxide emissions because we do not have to dump the waste at the dumping sites, but we produce compost. And at the same time, we can reduce mineral fertilizer use, thereby saving a lot of money. These are the stoves we are using. They are called NOAA stoves. As you can see, they're produced from locally available materials, usually from clay. They are top-lit updraft microgasifiers. They were invented by a German company called Prost, a clay production company. They are built from soil, sand, straw, and second-hand cans, and can thereby be produced for low cost. This is the concept of the top-lit updraft microgasifier. It means you fill a firebox with wood pieces or any other suitable solid biomass fuel, and you light it from the top, and then wood gas is produced. You reduce the airflow, and when the air meets at the top as secondary air together with wood gas, the wood gas is burned. So like the smoke is burned, they are smokeless, and we produce biochar at the same time because the wood is not completely burned but turns to biochar. Here you see the smoke when it's operated. You see the small wood pieces, they are lighted with a fire lighter from the top, and you see the flame on the right side that burns smokeless. This stove needs only 700 grams of dried and shaped wood, and with this you can cook 45 to 50 minutes, and it produces 150 grams of biochar per cooking session. It burns smokeless during cooking, but only it has a little bit of smoke when you stop it. And the outer surface doesn't heat, which is important for the kitchen safety. And we have 60% of fuel wood reduction. Thereby, we can mitigate 1.81 tons of carbon dioxide per stove in a year. And the biochar we produce fulfills the guidelines of the international standards like the IBR1 or EBC standards. For producing the NOAA stoves, we produce them from locally available materials for less than 50 euro per stove. We can produce 2,000 stoves per workshop and year. We create those workshops we can establish in the rural sites, thereby creating jobs. And we sell the stoves together with the wood because it has to be dry and ready shaped. So it's good if we sell the package together, because usually the households are not able to produce the wood by themselves. So we can exchange the wood for the biochar, thereby we can get the biochar back from the households. We already have a pilot workshop existing, so we are already producing those stoves. Together with the GIZ, the German Agency for International Cooperation, we made a feasibility study in Ethiopia where we distributed 30 stoves to different households in rural Ethiopia. And those stoves were well accepted. The women appreciated the smokeless and fast cooking, and all of them would have bought such a stove. And but it turned out that it's really important to produce the wood, to deliver it for the households and to get the biochar in return. When scaling up this approach, by establishing in the course of the years a lot of workshops in different parts of Ethiopia, we can mitigate and capture carbon dioxide, mitigating because we reduce the firewood demand, capturing because we could produce biochar, which we further on use in composting. So we can, within 10 years, we can capture and avoid up to 800,000 tons of carbon dioxide emissions only in the last year, in the 10th year. The biochar, why we want to use the biochar, most of you will know because you're familiar with the subject. The impact of biochar on composting is that due to its high porosity, it helps to prevent the leaching of the nutrients during the composting process. It increases the microbial diversity, thereby it increases the decomposition of the organic matter, and it decreases ammonia, methane, and nitrous oxide emissions. So we have an accelerated composting process with lower greenhouse gas emissions, which is good for a big composting site because you can reduce the time that you need for composting, for producing a safe and mature compost. On the other hand, when you look at the impact of composting on the biochar, you will see that biochar is stable during composting, like also in soil, it's stable carbon. It absorbs organic matter, thereby it gets loaded with nutrients. This increases also its cation exchange capacity, which is important for its further function in soil, because it can take and give back the nutrients to the plants, and it gets loaded with nutrients like nitrogen, phosphorus, potassium on its surface. So biochar is here important as a stable carbon in a nutrient and humus-rich compost as one component. So we use for composting between 10 and 20% of biochar. Thermophilic composting process then, with all these ingredients, are the buckets from the ecological sanitation, where we use sawdust. It's a water-free sanitation, where everything is collected together with sawdust, so we do not have any smell. We have the biochar from the stoves. We have straw. We can also use other manures, and we have the organic waste. This all has to be mixed in the right C to N ratio and the right moisture and right bulk density way. And then if you do this, you have a very fast rise of the temperature, up to 70, even 80 degrees. And this ensures that you produce a pathogen-free and safe compost, even when you use human excreta. So all human-related pathogens will be killed in the course of the composting process. This is what we could show. The potential here for climate change mitigation is we can avoid up to 50,000 tons of carbon dioxide in the 10th year alone, because we reduce methane emissions compared to the dumping of the organic waste at the dumping sites. Here in the beginning, we are just about to start a pilot composting site in Ethiopia, where we established a method, because we first have to define the baseline for all of what we are doing, so we can establish this method under gold standard. We could already show that with the compost we produce, we can completely replace mineral fertilizer. So we can use the compost in regenerative agriculture. And if we do that, if we use the biochar compost here, in combination with landscape restoration, we can mitigate, or we can even sequester carbon in soil and in trees up to 120,000 tons in the 10th year. Regenerative agriculture, landscape restoration, and agroforestry. Also here, we're just about to start pilot sites in another like in a scientific project approach to get this registered under gold standard. Thank you very much.